Hello everyone. Today we will build an artificial neural network to predict customer churn using Python and TensorFlow. We'll walk through the entire process step by step, explaining every single line of code. By the end of this session, you'll have a solid understanding of how to build, train, and evaluate a neural network using Python and some popular libraries. Let's understand the problem first. Let's say we have given a bank customer's details and asked to predict that would this customer stay in the bank or not. How will you decide? Probably by analyzing the details of the existing customers and the past customers who left the bank. You would be able to decide whether the customer will stay or not, right? Artificial neural network does the same thing. Look at this dataset of customers' detail, which includes credit score, geography, gender, age, tenure, balance, and so on. After analyzing this dataset, we may conclude that the customers with balance more than 1 lakh and the tenure of more than 4 years are more likely to stay in the bank. There could be several number of predictions we can make. We are going to build the model and train it on this dataset to predict the customer churn. You may wonder how the neural network works or learn to predict. Here is how it works. There are 3 layers basically: input layer, hidden layer, and output layer. There can be 1 or more hidden layers, and each layer can have a different number of neurons. In our problem, to decide whether customer will stay or not, we will use the customer details as parameters. For explanation purpose, here I am showing a few parameters only. In a neural network, neurons are the building blocks, much like how biological neurons make up your brain. Here, all these processing units are neurons. Each neuron receives signals from other neurons through connections. These connections have associated weights. Input layer receives the input data. Hidden layers process the data from the input layer and apply weights to the data. The weighted sum is passed through an activation function, which determines whether a neuron is fired or not. There are several functions used in neural network. Finally, output layer outputs the results of the network's computation. This process gets executed for each record of the dataset while training the model. As we have a basic understanding of how neural network works, let's start building one. Before we dive into coding, we need to ensure we have all the necessary libraries installed. These libraries provide the tools and functionalities required to build and train our neural network. Pandas and NumPy help us manage and manipulate data efficiently. Matplotlib and Seaborn are plotting library used for creating static, interactive, and animated visualizations in Python. Scikit-learn for machine learning utilities. It features various classification, regression, and clustering algorithms. And TensorFlow provides a high-level interface to build, train, and evaluate our neural network. Next, we load our dataset. This read CSV function from the Pandas library reads a CSV file and loads it into a data frame. Then, we're creating our feature matrix X and target vector Y. X contains all columns from the 4th to the 2nd to last, while Y contains just the last column, our target variable, exited. The values attribute here converts the data frame to a NumPy array. We can take a look at the dataset we loaded. This head function returns the first 5 rows of the data frame, allowing us to quickly inspect the data. We can see our dataset is loaded properly. We can also check for any missing values. This code will print out the count of missing values for each column, helping us identify if we need to handle any data cleaning. As we can see in our dataset, there are no missing values. Now, let's visualize our data to gain some insights. In this block of code, we are creating several visualizations. There are several methods available in these libraries using which we can create different types of charts, histograms, and plots, etc. Here we create histograms for geography, credit score, and age distributions. These visualizations help us understand the distribution of our data across these features. Here I have created more visualizations to explore relationships between different features. These box plots and count plots help us visualize relationships between different features in our dataset. Now, let's pre-process our data. The dataset contains categorical data that needs to be converted into numerical format for the neural network to process it. We will use label encoder and one-hot encoder for this purpose. Label encoder encodes categorical features as integers. Here we are converting the gender column into numerical form. And here we're using one-hot encoder to one-hot encode the geography column. One-hot encoder encodes categorical integer features as a one-hot numeric array. we are setting sparse output to false for compatibility with newer scikit-learn versions. This 1 represents the column number we want to encode, which is geography in our case. And this remainder parameter ensures that all remaining columns, other than the first column of geography, that were not specified in transformers, but present in the data passed to fit, will be automatically passed through. The column transformer allows us to apply this transformation to just the specified column while leaving the others unchanged. The fit transform method fits the one-hot encoder and transforms the data into a one-hot encoded array. Let's print the values of X and Y to look at the converted values. As we can see, the first record with geography France having a value 100 instead of the string France. Similarly, for the second record, it converted the Spain to 001 numerical value. And last second record with Germany is 010. Next, we split the dataset into training and test sets to evaluate our model's performance. This train test split function from scikit-learn splits the data into training and test sets. In this function, we are passing the value of X and Y and setting the test size to 0.2, which means that the 20% of the data will be used for testing, and the remaining 80% will be used for training. And the last parameter, random state, ensures reproducibility of the results by initializing the random number generator with a fixed seed. Basically, it controls the shuffling applied to the data before splitting it. This can be useful for debugging or for ensuring that your results are reproducible. You can set any integer value here. I am setting it to 42. We then scale our features to ensure they are on the same scale, which helps the neural network to converge faster. Standard scaler standardizes features by removing the mean and scaling to unit variance. This is crucial for neural networks to work effectively. The fit transform method computes the mean and standard deviation of the training set and applies the scaling to it. And the transform method applies the same scaling to the test set based on the parameters computed from the training set. Okay, now it's time to build our neural network model. We will use TensorFlow and Keras to build a sequential model for our binary classification task. First, import the necessary components. Sequential is a linear stack of layers and dense is a fully connected layer, where each neuron in the layer is connected to every neuron in the previous layer. This sequential method initializes the neural network model as a sequence of layers. In input layer, we are setting the value of shape to the input shape argument. This line specifies the shape of the input data. The input_shape parameter should match the number of features in our dataset. Next, we add the first hidden layer. We use the dense layer with 64 neurons to define the number of neurons and the activation function. The ReLU, rectified linear unit, activation function introduces nonlinearity to help the network learn complex patterns. This dropout layer randomly sets 50% of the input units to 0 at each update during training, which helps prevent overfitting by reducing the model's reliance on specific neurons. Similarly, we added second hidden layer with 32 neurons and ReLU activation. Finally, the output layer adds a fully connected layer with 1 neuron and uses the sigmoid activation function. The sigmoid function outputs a probability value between 0 and 1, making it suitable for binary classification. Finally, we call the method to build the model, passing the input shape as a parameter. Here, this shape method sets the input shape for the model based on the number of features in our training data, x_train. Now that we have built our model, the next step is to compile it. First, we need to import the additional components required for compiling the model. Atom is an optimizer that computes adaptive learning rates for each parameter. It's efficient and widely used for training deep learning models. Early stopping callback monitors a specified metric and stops the training process if the metric doesn't improve for a set number of epochs. This helps in preventing overfitting and reduces unnecessary training time. Compiling the model involves specifying the optimizer, the loss function, and any metrics we want to track during training. Additionally, we can set up early stopping to prevent overfitting. The Atom optimizer is used with a learning rate of 0.001. The loss function used for binary classification. It measures the difference between the predicted probabilities and the actual class labels. The goal is to minimize this loss during training. With metrics parameter, we can track the accuracy of the model during training and evaluation. Accuracy is the ratio of correctly predicted instances to the total instances. We also set up early stopping to monitor the validation loss and stop training if it doesn't improve for a specified number of epochs. Monitor specifies that we are monitoring the validation loss. The training will stop if the validation loss does not improve. Patience specifies the number of epochs to wait for an improvement in the monitored metric, validation loss, before stopping the training. If the validation loss does not improve for 10 consecutive epochs, training will stop. And setting restore best weights to true ensures that the model weights are restored to the best weights observed during training, which prevents overfitting and makes sure the model is as good as possible. Finally, we can print a summary of the model to see its architecture and the number of parameters. The summary function prints a detailed summary of the model architecture, including each layer's output shape and the total number of parameters in the model. This is useful for verifying the model structure before training. Now that we have built and compiled our model, it's time to train it using our training data. Training a neural network involves feeding the training data into the model, allowing the model to learn patterns, and then evaluating its performance on a validation set. We are using the fit method in Keras to train the model. It returns a history object, which contains the training history, including the loss and accuracy metrics for both the training and validation sets. We store this in the history variable. In this method, we are passing input features xtrain for training and the target labels ytrain. Setting epochs to 200 specifies the number of times the entire training dataset will be passed through the network. We set it to 200, but training might stop earlier due to early stopping. The batch size defines the number of samples that will be propagated through the network at a time. Here, we use a batch size of 32. The validation split specifies the fraction of the training data to be used as validation data. We are using 20% of the training data for validation. Callbacks use the early stopping callback to halt training when the validation loss stops improving. And finally, the verbose controls the verbosity of the output during training. Setting it to 1 means that progress will be displayed for each epoch. We can notice that the accuracy is improving over epochs, and the loss is decreasing over epochs for both training and validation datasets. As we are using a small dataset of 10,000, our model gets trained quickly, but when we train the models for real-world problems, the dataset would be very large, and it takes much longer time to train the model. We can visualize the training process by plotting the accuracy and loss over the epochs. Accuracy plot shows how the training and validation accuracy change over epochs. We expect to see both accuracies improving during training. And the loss plot shows how the training and validation loss change over epochs. We expect to see both losses decreasing during training. After training the model, the next step is to evaluate its performance on the test data. This will give us an idea of how well the model generalizes to new, unseen data. This evaluate method evaluates the model on the test data. It returns the loss and accuracy of the model on the test data. As we can see in our case, the loss is 0.3327 and accuracy is 0.8630. A lower test loss indicates that the model's predictions are closer to the true values. And a higher test accuracy indicates that the model correctly predicts the outcome, customer churn, for a higher proportion of the test samples. Finally, let's use our trained artificial neural network model to predict whether specific customers will leave the bank based on their information. The predict method predicts the probability that each customer will leave the bank. Scalar.transform scales the input data using the same scalar that was used to scale the training data. Each customer is represented by a list of feature values. In P1, we are passing 001 for Spain, credit score of 608, 0 for female, and so on. Let me run this code first. We can see the predicted probabilities are 0.16, 0.21, 0.87, and 0.03. Here we are checking if the predicted probability is less than 0.5, indicating that the customer is predicted not to leave the bank. A prediction of less than 0.5 means the model predicts the customer will stay, while a prediction of 0.5 or greater means the model predicts the customer will leave. Accordingly, from our output, we can say that the customer P3 with the probability of 0.87 would leave the bank and all other customers would stay in the bank. And that's it for the video. Now you have a good understanding of building, training, evaluating, and using an artificial neural network to predict customer churn. I hope you found this walkthrough helpful and informative. Please like and share the video. Subscribe to the channel for more AI content. If you have any questions or need further clarification, feel free to ask in the comments below. I will see you in the next video. Till then, happy coding!